All right, we are continuing our sixth geometry topology summer school in our second week. Our first speaker is Fino. She's going to talk about interplays of complex and symplectic geometry.
So thank you very much for the invitation. I am glad to give this for lecture, and it's a pity that I cannot go there, but anyway. So the idea is to speak about interplays of complex and symplectic geometry. So I will give an idea at the beginning what is complex geometry and symplectic geometry, and we'll see the interplay in this way. So we'll see links between different objects, and the manifold will be even dimensional. So the manifold will be 2n dimensional. And the idea is the following. So we will see geometric structure like almost complex structure or symplectic structure. Okay. And the idea is to see the interplay property of almost complex structure or symplectic structure in terms of the existence of special Riemannian metric, so metric which have special property. And we will see that often this translation in terms of metrics turn out to be a translation on solving PD equation. Okay. In particular, in the free lecture, we will see this topic. So the topics that we will see will be the timing condition, which is a condition which relates the almost complex structure with the symplectic structure. And we will see that this translates in the complex case in a special type of metric will be the pluriclause matrix. Okay. And today we will focus on this, on the first part, this, and then we'll see also the symplectic Calabi-Yau problem. We generalize the, let's say, the usual Calabi-Yau theorem. And in the last lecture, we will see a little bit about balance matrix, Mikan matrix, and Strominger system. We will see that this one is also related to the Calabi-Yau condition. Okay, so let's start with the first topic, and let's start with review a little bit about complex structure. So what we have an almost complex structure. Okay, what is an almost complex structure on our 2n dimensional manifold? And 2n is just an endomorphism. So J is an endomorphism on the tangent space of our manifold such that J squared is equal to minus identity. In particular, we have the case when J is induced by our manifold M2n, which is a complex manifold. This is a special case because in this case, we have an atlas, okay, U alpha, let's say, with map phi alpha from U alpha to an open on Cn, and we have transition function, which are just, let's say like that, which are the form phi alpha decompose with the inverse of phi beta, okay? And let's go from phi beta u alpha wedge u beta in phi alpha wedge u alpha wedge u beta. And what you ask, these are holomorphic map. So locally, what we have a holomorphic coordinates. Let's call zeta 1, zeta n, and denote by x alpha, the real part, epsilon alpha, the imaginary part. And what happened that, in fact, when you have such situations, so a complex manifold, you have in a natural way an induced almost complex structure, just defined by J, the X alpha is the epsilon alpha, and J, the epsilon alpha is minus the X alpha. Okay, that's a picture. And there is a nice theorem famous theorem by Blonder, Nirenberg, that say us when exactly J is induced by a complex structure. To be induced by a complex manifold structure is also say that you can say that J is integrable. So we say that an almost complex structure J on our manifold is integrable in the sense that is induced by a complex structure, in the sense that I wrote before, if and only if. One can see this in analytic terms, just asking that the Ninoyos tensor is 0. And here for the Ninoyos tensor, we just mean in J, two pair of vector field x, y. By definition, it's just minus the bracket of x, y minus j, x, y minus j, x, y plus the bracket of jx, jy. So, of course, we ask that for any x and y to be 0. And this is an analytic condition. And what we are saying here is essentially that if you take the bracket of 1, 0 vector fields, of course, you have the 1, 0 part and the 0, 1 part, which correspond to eigenvalues I and min y corresponding to j. And then here, what you ask, the bracket of 1, 0 vector fields is still of type 1, 0. One can see this condition in terms of differential when we have so here we talk about complex manifold when our almost complex structure has an Ninoyos tensor equal to 0, that is equivalent as we saw, and when one considers the differential D, okay, the natural differential, the differential split in the integrable case as D plus D bar Okay, and if I look the condition d square equal to 0, this means automatically using that d split as d plus d bar, it means that d square is 0, like d bar square 0, like d bar plus d bar d, all right? So we have d bar square equal to 0, and that's allowed to define this is not the only type of cohomology that one can consider, but one can consider, we'll see, more cohomology that we can consider on a complex manifold. Anyway, this defines in a natural way what is called double cohomology, which is just, so type PQ, let's just write this star M d bar is just, so if this P and Q, this is just the kernel of d bar from the form type PQ to the form of type P, Q plus, right here, plus 1 over the image of the bar, okay, from the correct space. Okay, so now we know what does it mean to have a complex manifold. And as I said at the beginning, one can see property of complex manifold in terms of spatial metric. And we will see that type of spatial metric, dimension 2, complex dimension 2, complex dimension 1, real dimension 2, you have always this type of metric, the Keller matrix. So we will see that, let's write like that, some complex manifold are more complex than others. Let's say in this way, roughly speaking. And the first thing that we define, what does mean that you have a metric compatible with the complex structures, or orthogonal with the complex structure. So we define the notion of a Hermitian metric. So let's keep this definition. We have a Riemannian metric. So Riemannian metric G on our complex manifold. One can, here in this definition, you don't use the integrability of J, so it also, so if J is not integrable, is called J Hermitian. Okay, or also compatible with J if essentially you have the orthogonality point by point. So what you ask is that in any point P or your manifold, if you consider the scalar product on the tangent space and Ju, Jv, where U and V are tangent vector to your manifold, then you have that Gp, Ju, Jv is equal to Gp, UV. Okay, so you have this type of orthogonality. In fact, one can say that J is orthogonal with respect to G, to the Riemannian. Using G, the pair J and G, one can define in a natural way two forms. So let's see this remark that we can define the two form in this way. So we have two arguments and it's Q-symmetric in the argument. And by definition, this is just a convention. So we define a G, J, the first argument, and then the second argument. Okay. What happened from the property, from this property, from the orthogonality, that this is a true form. Okay. But it's not only a true form, but it is a true form of type 1,1. What does mean type 1,1? It means that omega is J invariant. So if you apply J in both the argument, okay, you get the same values. And the important thing here that omega is non-degenerate. So that means that if you do the wedge product, so here with this notation, I will always denote the wedge product of omega and times. This is non-zero, give you volume form, in fact. And then you have, let's say, an isomorphism between T and T star using that. And we will use this name. Omega is called the fundamental form okay, of the pair JG, which is also called Hermitian structure, or almost Hermitian structure if J is not integrable. And the nice thing here that you have 3 objects, but choose the third one, okay? So you can play in this way. So let's see examples. Let's start with some example. So of course, the more simple case is when n is equal to 1, then we have Riemann surface, right? And in this case, since you have a 2 form, you are in the real dimension 2, every 2 form is close. Okay. And we'll see, in fact, a difference between n equal to 1 and the higher dimension. Another case, very simple, is Cn. Okay, the standard case, locally, a complex manifold is a local copy of Cn, in fact. And here we have the natural flat, let's say omega flat, which is just given sum j equal from 1 to n, I over 2 z zeta j wedge d zeta by j. This metric, okay, here you have the standard complex structure. We will identify often omega flat with the metric, and this metric induces in a natural way a metric on Cn over a lattice gamma, which is just a copy of zeta to n, okay? And this is just a complex, the case of a complex array, okay? And that is diffeomorphic to n to n copy of S1. And the metric there is just induced by the flat metric, remain flat. Then we have the case of complex Rieti space. And again, we have CPN, okay? The construction of CPN, CP1 is just a copy of S2, okay? And here we have the Fubini study metric form, which locally one can write, like, let's write here, like sum I, or let's write explicitly, like here, E the bar of log 1 plus, and then you have the sum J1 modulo J square over zeta 0. Here I am using just projective coordinate zeta 0, zeta n on CPN. Okay, in fact, the example that we saw that here have the property to be Kähler. All the time, the fundamental form is closed. That's exactly the condition to be Kähler. So let's give the definition, okay? definition. If you have MJ, complex manifold, G, an Hermitian metric, G is scalar if the fundamental form is closed. So in particular, that means that the omega give you a symplectic form because you have a closed T2 form, which is non-degenerate. So the first question that one can ask is, are all the complex manifolds scalar? Okay, so the question is no, for general, for n bigger than 1, for n equal to 1, all Riemann surfaces are scalar, just because you have a closed to form. And so in general, for n bigger than equal than 2, there are some necessary topological conditions. Okay, for in the compact case, so for compact manifold, here I just mentioned some of them. For instance, the odd Betti numbers, or your compact manifold has to be even. Also, the fundamental group of your manifold has to be of special type. There is quite a lot in the literature about that. And another property, very important property, is the formality. So the manifold has to be formal in the sense of rational homotopy theory. Okay, to be scalar or non-scalar, the situation is a little bit special for complex surfaces. In complex dimension 2, there is a theorem, famous theorem. This famous theorem, which is in one direction, was proved by Kodaira. And then by Siu in the other direction. And then more recently, there is a different proof by Buchtal and independently and Lamoury, and the theorem is the following. So n equal to 2 is special in the sense that the necessary condition that I wrote before, that B1 is even, is also sufficient. So what happened is that a compact complex surface is scalar if and only if B1 of M is even. So the necessary condition that we wrote before is now sufficient. And the proof, in fact, the proof given by Kodaira used the classification by Kodaira of complex surfaces. And then there is another proof due to Buchtal and Lamoury that use currents. Later we will see the notion of currents. How in some case, some Hermitian metric can be characterized in terms of currents. Okay. So let's see an example now, a non-scalar example that we'll see later also in the next lecture. Very simple example. The example that we see now is the Kodaira-Thurston manifold. It's called this way because it was described by Kodaira and then by Thurston. And it's very simple, this type of example, which is special type on Hill manifold. we'll see what that means. So we have 4 manifold, real dimension 4, which is a quotient of G over a lattice. Okay, here I will describe what is G. The group G is an important group, and gamma, which is a dice-crystal group, such that the quotient is compact. G is just the product of Heisenberg, real Heisenberg, dimension 3, which will denote also we need 3 times R. Okay. So if we want, we'll call also, let's call this H. So H, the 3-dimensional, is just the group of an important matrix, so this form. So we have 1 in the diagonal, 0 here, and then we have X, Y, theta. Let's order in this way. No, sorry, let's change this because I will use this order. So X, Y, theta, where X, Y, theta are real number. Okay, and our gamma essentially is a lattice, is the product, is a copy of theta 4, and essentially it's the product of a lattice here that you get just taking X, Y, theta integer. Okay, just a product like that. And what is, so M4 is special example of what is called in the literature compact manifold, since it's a compact quotient of a simply connected important group by lattice, and is parallelizable. So you have a global frame, coframe. I will write here that it just essentially is just given by 4 in this case, left invariant one form, which are independent. Okay, so we have a global, let's write like that, and 4 as a global invariant coframe. So this is something that is at the level of the group, but is inducing one form on M4, the compact quotient, EI. And now we will write the expression of this EI, just small computation. So we will have, these are all invariant. I will order in this way. We use this order also later. E1, dy, E2 is the X, E3 is the T. One can check that these are all invariant. And then you have an extra terms here with the zeta to get that invariant. You have to subtract X dy. So what we have, and I will use this notation, that here we have that the first 3 one form are closed. So I will use this notation to denote the E1, E2, E3. And the 4 one, if you compute the E4, you can see that it is just the X minus the X with the Y. And so I will denote that this is just U1 by U2, and I will denote with this notation 1, 2. I will use this notation later for groups. And the important thing here that M4, it was an interesting example because it's both complex and symplectic, but not killer. Why is not killer? That's easy to check in this case because we can check that B1 and 4 is just free. Why that? Because it's a general result by Nomitsu theorem that when you have an ill-manifold, so you have a compact quotient of a simply connecting important group by lattice, and you compute the ramp homology there, this is isomorphic to the Chevalier-Eilenberg homology of the Lie algebra of G. Okay, so if you want to compute the B1, it's just a number close, independent closed one form that in this case is free. So we have automatically that it's non-killer, and to construct in a natural way a complex structure, that's easy because you just work at the level of the algebra. For instance, you can take J, E1, defined as E2, J3 as E4. This is at the level of the Lie algebra, but then this induces a last invariant complex structure J on the group, and then you have something which is invariant, induce something on the manifold, on the compact quotient. Okay, this is what usually one call as invariant complex structure on a compact quotient like that. That means something which is induced by a complex structure at the level of Lie algebra. And the same for symplectic structure. One can define in natural way symplectic structure that we consider also later. So a two form which is closed and non-degenerate, and one will take omega equal to E1 wedge E4 plus E2 wedge E3. And then it's easy to, if you check, you see that the omega is 0, okay? And omega square is different from 0. We will use this when we'll talk about symplectic labial problem for this type of surfaces. And so what we have that this is M4 is an example of what is called Nien manifold, company manifold. In particular, is an example of compact, not homogeneous space, but locally homogeneous space, because you have only the property locally homogeneous. Okay, that's what I mean for compact locally homogeneous in a specific case. And there is a nice result due to Hasegawa, very interesting. He's studying the complex structure, more general, what they are called compass on manifolds, okay, which are complex dimension 2. So instead of considering an nilpotent group, you consider a solvable group, which is a bigger class. And it shows that in case of codilators on surfaces, every complex structure on M4 is in fact invariant. So it is induced. This is not the case in eigendimension, but this is true in the case of codilators on surfaces. Okay, so for the moment we see two notions, the notion of complex manifold and the notion of symplectic manifold. Okay, you have those M2 and with a symplectic form, omega. So here we have this. Okay. In fact, almost complex manifold. Let's see which property we have. Okay, let's write again the property that we have between J and omega in the killer case. And let's weaken this condition a little bit. So for a killer manifold, and this will give us the condition to be tame. We'll see how it's defined. So for a killer manifold, we can write all the condition in this way. This is just a killer form. So we have d omega 0, okay? Omega non-degenerates. So as we say, omega gave us symplectic form. And then we have that the compatibility. So omega is of type 1, okay? So it's J invariant. Omega is positive, so define a Riemannian metric, G, okay? And the last property to be complex is the Ninoy's tensor is 0, so complex. Okay, in the lecture, we will see essentially two types of generalization that we can have. The first type of the generalization is due to Gromov. Okay, it's more general for almost complex structure. And in fact, what you ask is essentially that omega is not anymore of type 1,1, but you have a symplectic form whose 1,1 part, okay, is positive. So this is a little bit weaker condition. That's definition due to Gromov obtaining condition. So if we have it holds in general for an almost complex structure. So let's take an almost complex structure J on our symplectic manifold. So we have M2N omega, which is symplectic, is tamed by omega, or omega is tamed in J, the same thing. If, as I say, the 1,1 part of omega is positive, that means that if you take omega x, j, x, okay, this is positive. So it's defined a metric, Hermitian metric, almost a Hermitian metric for any x non-zero. In fact, how is the metric that you can define if you have j is tamed by omega? We have a natural metric that we can define. This is just given by g, x, y. And then you define using the 1,1 part. So you have 1/2 of omega x, j, y minus omega jx, y. Okay, this is just a 1,1 part of omega. And this is J Hermitian. So it's compatible with J. So anytime you have a symplectic form taming an almost complex structure, you have again a metric, like in the killer case. The difference with the killer case is that Nj is 0, so you have a complex manifold, and in the killer case, omega is of type 1. That's the main difference. Okay, now we'll consider the case when Nj is 0, and you have the condition that J is tamed by omega. So the combination of these two, okay, for complex surfaces. There is a theorem due to Ritz and Tian and independently was shown by Li and Zhang that complex surfaces are in fact spatial, because if a compact complex surface M4J, so 4 is the real dimension, has a symplectic form timing J, then M4J is a Kähler metric. So you don't go far from to be Kähler. And the two proofs are given with different methods. Ritz and Tian, I just give an idea what to use. Ritz and Tian, they use in fact the signature theorem for compact complex surfaces. And then there is another proof by Li and Zhang, which is more using symplectic stuff, and in fact are using the cone. The cone, we'll see later a little bit about the Kähler cone, and they generalize what is called the Kähler cone in the symplectic case as calibrated cone or tail cone. Okay, but I want just to give an idea about what is the idea of Ritz and Tian. Essentially, they use Ritz and Tian use the signature theorem that means then the intersection form of a non-killer, let's say like that, complex surfaces has to be is negative. Define. Okay. The intersection form is just you use the integral of the wedge of your let's say the fundamental form, non-killer associated to your non-killer complex surfaces. And what happened, that's the only part that essentially Street and Tian proof. They show that if you take omega, the class corresponding to omega 1, so the which is positive, okay, this has positive self intersection, and that's why they get essentially the result. The other proof, which is also nice, is using essentially the taming. The other proof by Lee and Sang, using the taming and calibrated cones. We will see a little bit later about killer cones. Okay, so for n, let's say that for n complex dimension n equal to 2, essentially to have a symplectic form taming a complex structure is more or less the same as scalar, all right? So the natural problem is what happened for n, complex dimension n bigger than 2. That's exactly the problem. We'll see some result in this direction. So the problem, the natural problem is thus there exists an example of compact complex manifold with n bigger than 2, which has a symplectic form omega taming J, but no killer. Non-killer structure. This is still open, completely open. So it's in fact is an open problem, and we'll see some negative in some case, some negative answer. All the possible manifold that one when tests this problem, in fact, where there was no possibility to find a counterexample, so maybe it's true, we don't know. Okay, the first thing, let's try to translate this problem. So to have a symplectic form taming J in terms of Riemannian metric, as I said at the beginning, that's not easy. That's easy in some sense, because given the first remark that one can do, that giving a symplectic form omega taming J is exactly equivalent to impose that. You just use this, you can decompose omega in the 1 part, 2 0 part, 0 2 part. Okay? If you use this decomposition, you use the omega 0. Okay, what you have, that you have the d, you can translate in this way, d omega 1 1. This is just an exercise. You use d equal to d plus d bar, and then you apply to that, and what you get, the d omega 1 1, which give you the metric, is d bar exact. Is the bar of, let's say, a beta 2 0 form, which is d close, is in fact this beta, if you use that, it's just minus omega to 0, essentially. But you can see that you have this property, that d of omega 1, 1, which is the fundamental form, your metric is d bar exact, and is d bar of beta, where beta is the close. Okay, so this makes the definition of what is called a pluriclose metric. That's the first, the title of the lecture was taming condition and pluriclose metric. In fact, from this, you can see that if you apply the bar of the omega 1, 1, this is 0. Okay, so now I will define what I mean for pluriclose or SKT. These are also called SKT in the literature, strong Kähler torsion metrics. Let's give a definition, more general definition. So Hermitian metric G on our complex manifold is pluriclose or SKT if you take the fundamental form, d bar of the fundamental form is 0. d bar omega is 0. Okay, you can write this as e d bar omega to be 0, and you can read this condition in terms of the operator dc. So you can see, you can write as d dc omega 0, where dc is just the operator given by minus j inverse, okay, dj. That's how it acts, and in fact is minus e d bar minus del. That's the operator. And in fact, you can see the ddc 0 is exactly equivalent to d bar from this expression. Okay, the first remark that one can do, if you look at this condition in terms of omega, the pluriclose condition, you can, we'll see in the last lecture, the condition to be balanced, for instance, is again a condition on omega, right? Some condition on omega, which is different from condition to be omega declose, which correspond to Kähler. But the pluriclose condition is, in some sense, is the only, let's say, weakening of Kähler condition which is linear in omega. Okay, because you apply just this operator d bar. Okay, what we can say about this pluriclose metric? Again, the picture is completely different from complex dimension 2, a higher complex dimension, due to a theorem by Duchon that say that in the compact case, if you take a compact Hermitian, so J is integrable, then he showed that there exists a unique function, infinity function on your manifold, such that, okay, you have this condition, not directly the bar of omega 0, but if you do the conformal change, so if you do this conformal change, a exponential of 2u, which is positive, multiplied by omega, okay, and you do the wedge of this n minus 1 times, then you get something which is d bar close. D bar of that is 0, okay, and the unicity, we wrote here that is unique. The unicity is just given by this integrable condition. If you take the integral over your manifold or U, this is just the volume form, dvg associated to G, this is 0. Okay, so we will say what we are saying here, that in the conformal change, I think Alexander Ottoman will talk more about conformal change, locally conformal condition, and so on. But anyway, if you do a conformal change of your omega, okay, in the conformal change, you can find a new metric with this property. That's what we mean. So that means that every conformal Hermitian, let's say, structure on compact complex manifold contains a Hermitian metric omega tilde, such that this is what we are saying, right? The bar of omega tilde L minus 1, which power is 0. Okay, so that's a good point, because for n equal to 2, right? What they say that if you take a compact complex surfaces, you always have a pluricross match in the conformal change. So every compact complex surfaces for n equal to 2 has a pluricross match. So the intrinsic case for looking pluricross metric is n bigger than 2. Okay, the first thing that we are doing here is to rewrite this condition to be for omega to be TD bar close. We will rewrite in terms of connection what is called in the literature the bismuth connection. We will write a little bit that, and that's why it's also called SKT, strong with Kähler with torsion. And to see that, see this condition in terms of the bismuth connection, let's introduce the bismuth connection and the Chern connection and so on. So let's introduce this theorem that is again due to Gürsey. And it's quite important theorem because say that, okay, when you look in the Kähler condition, I didn't write the condition, but for the Kähler condition, you have that the Levchivita connection preserve both the complex structure and the metric, right? When you are in non-Kähler geometry, you have again some special type of connection that's called Gürsey connection. And in fact, Gürsey showed the following. On any Hermitian manifold, there exists an affine one parameter, let's say, line of canonical Hermitian connection. I will explain in a moment what I mean for Hermitian connection. They depend on parameters. So let's note nabla tau. Tau is a real number. And we have the condition that nabla tau j is 0. Is parallel with respect to nabla tau. And also the metric is parallel. So preserve the complex structure and preserve the metric. And tau is in R, which is completely this family. Every element of this family are completely determined by the torsion of the connection. And in fact, we will use, instead of using the torsion with the two arguments, okay, x and y, we'll use torsion using the metric with the free argument. So we will use this identification. We will use t, x, y, zeta. I will denote again with t, like g. And this is the usual torsion, okay? T, x1, so nabla xy minus nabla epsilon x minus the bracket zeta. We use this identification. And all the elements of this family is determined by a condition on the torsion. One can write, in fact, the family in this way. Nabla tau is tau nabla 1 that we describe is just a chain connection. I will describe in a moment, plus 1 minus tau nabla 0. Okay, so how is characterized? This is nabla, which is the chain connection, is defined also for almost Hermitian case. We'll see how, and it's just characterized by the condition that the torsion TC, T-chain, let's say, is 1-1 component, trivial. So vanishing the 1-1 component of the torsion. And here is the other way around, this nabla 0 is torsion of type 1-1. So you see the two extremes of the family, the chain connection, which is vanishing the 1-1 part, and the other, which is only type 1-1. But inside this family, if you take tau equal to -1, you have the bismuth connection. The bismuth introduced for proving some index theorem for non-Kähler geometry. And this is a nice property, because as a property, you see the torsion we define three arguments, x, y, and zeta. And nabla, the bismuth connection, is characterized by the property that the torsion TB is a free form. So by this definition, you can see that it's Q-symmetric only on x and y. And you are asking here that it's Q-symmetric in all the arguments. So it's a free form. Good. So that's, one can write explicitly our explicitly given these two connections in terms of the bismuth connection, the chain connection in terms of the Levchivita. That's easy, because you just take this bismuth x, y, theta. The difference that determines the torsion, essentially, right? The difference between our connection and the Levchivita connection give us the torsion is just given by that. 1/2 dc omega x, y, theta. So the torsion is just dc omega. Okay, you can see that this is a free form, in fact. In the case of the chain connection, our chain connection, which is nabla 1, we have G, nabla again, and here the difference, one can really compute that, it's not difficult. It's just 1/2 of T omega, and then in the first argument you apply J. Yes. All right. So if we come back to the expression here, this. Okay. Remember I was so this is like our TB, the torsion, right? The condition to be pluriclose was DDC omega 0. So in translate the pluriclose condition in the fact that the torsion of the bismuth is closed. Okay, so to remark that we have here that G is pluriclose if and only if the torsion of the bismuth connection is closed. And that's why it's also called scalar geometry with torsion and so on. Okay. There is another thing that one can do. If you take the chain connection, okay, and you take this trace, let's take this trace. So to x, you associate the trace of this operator, epsilon, and then you take the torsion or the chain connection. Okay, this one. This trace is equal to what is called the leaf form that I will use, but also Alexander, I think he will use quite a lot, the leaf form, theta, that one can show is a walk form, is exactly that trace, and is equal to J, the operator, the D star, operator apply to omega. Okay, and this is important because this is the unique one form such that if you look again this omega n minus 1, you apply the differential, this is equal to theta wedge omega n minus 1. That's characterized in a unique way, is a unique one form such that you have this property. And having property about theta, the term property of about your manifold. Okay, so I talk about pluriclose metric. Let's see example. The first examples that one can look are the even dimensional real compact real groups. We'll see that are interesting, but are not so much interesting because, in fact, in this case, a Bismuth connection will be 0. So let's see this example. So let's say G with take a compact real Lie group, okay, of even dimension. Let's consider G, the Lie algebra of our group G, and let's consider the, so we take the complexification, GC, okay, or G, and let's say the Cartan subalgebra of that. So denote by TC, okay, by notation, the Cartan subalgebra of ZC. What does it mean? That in the semi-simple part, you just have a maximal abelian subalgebra, okay? By Samuelson, that's a nice result by Samuelson, that construct in a natural way on G, a left invariant complex structure. In this way, he showed that left invariant, let's say like that, complex structure J on G is equivalent to give a pair. So you work in two parts. You work on the part corresponding to the Cartan subalgebra. So let's say J, T, okay? And in another part that is in the roots part, P, with what we have. J, T is just any complex structure on T, right? And P, so the complex structure is a term by choice of a positive roots. So P is just, let's say, a system of positive roots. Using the Cartan subalgebra, you have your roots, and then you choose a choice of positive roots. And then, okay, when you want to define a J, it means to define the 1-0 vector fields, essentially, that's standard. So you define the 1-0 vector on G, and this is defined by this choice of 1-0, okay, vector on T plus just the sum with alpha, which is just positive roots, and then you have the complexification or your root space. Okay, how we obtain, how we get the pluriclose metric? That's easy because let's consider GG. Okay, this is the correspond to the semi-simple part of G, essentially. So what we can take here, since it's semi-simple, we just say the negative. We consider the negative of the killing form, because the killing form is negative. Okay, on GG, we consider that, and we extend to a positive scalar product on G, okay, which is compatible with J, so we consider that and we extend it to, let's say, a J compatible positive inner product. On your Lie algebra. And what is going on that using that, the Levi-Civita connection, if you compute the Levi-Civita connection, this is just given by the bracket. It's just 1/2 of the bracket, x and y, for any x and y in the Lie algebra G. Okay? And now we want to see how is the bismuth. The bismuth connection is very simple because you just define what you consider nabla, okay? Just give 0. So nabla, if we take nabla x, y, 0 for any x and y in G, right? We have automatically that nabla G0, nabla J is also 0, okay, by a direct computation. And the torsion, if we compute the torsion of that, okay, here is easy because nabla is 0, so it's just minus the bracket, right, of x and y. And so the torsion with free argument of this connection is just given by minus g x y bracket scalar product with zeta. All right, and this is a closed, that's an exercise, is a closed free form. Okay, so what we have, that we have this, the nabla that we define is just the bismuth connection. And the torsion is closed. So we have that our G is a pluriclose metric. This particular example is also interesting for generalized scalar geometry because Skiv also is maybe the more simple and the first example of what Gualtieri introduced and Lichin of generalized scalar structure, because you just take a combination, you take the left invariant complex structure and you play with the right invariant complex structure, and then you can define what is called generalized scalar. So you have a bi-Hermitian structure. As I remarked, this is, in this case, is flat, okay? I think maybe this is a good point to stop probably. And next time we'll see non-flat example, okay, with pluriclose metric, characterization in terms of currents and so on, and it will give negative answer to the problem that I say. Okay, maybe I stop here. I think I finished the 20 pages, and I can use some time to if the people is not tired to see more example, but as you like. Okay, I have still energy to write something more.
All right, thank you very much. Any question?
May I ask a question?
Yeah, sure.
Okay, thank you for this nice talk. I am Yup. I wonder, you mentioned about the torsion. Torsion is the skew symmetric, but I remember from the notes of Agricola, I don't remember exactly, the torsion have 3 independent parts, I guess, vectorial parts, skew symmetric part. This one is assumption for this one, or directly in
Yeah, it's true. In general, you have this result by Erika Agricola and Thomas Friedrich and so on. The torsion has more parts. And what you were asking here for the bismuth connection,
yes,
that you have only the torsion is free form. For instance, they characterize them saying, as far as I remember, that the geodesics are,
okay.
This is what they call metric connection with torsion. So it's a special type of metric connection with torsion. The only additional property is that preserve also the complex structure. But if you impose that the torsion is Q-symmetric, you have only one connection in Riemannian geometry. And that's exactly the condition for geodesics to be the same as geodesics of the Levi-Civita. I think they study, there are nice, the nice lecture that I think Ilka Agricola gave on this case, on this connection with torsion from Riemannian metric point of view. Is a special case, right?
Okay, thank you. Thank you so much.
Yeah. Yes, so that's it's called, in fact, it's called bismuth or Strominger, because we'll see that also Strominger we use, but it's in fact a metric connection with torsion. Yes.
Okay, okay, thanks so much. I got it.
Welcome.
All right, any other question? Okay, so thank you very much, Anna. For
Thank
nice
you. You see that I use all 20 pages.
Yeah, right. Yeah.
Yes.
Nice place to stop. Yeah, exactly.
Yeah, no, that's a good place.